This video is a follow-up to the previous one where I made a dune crisp knife out of bronze, but I did it a little differently this time. While most people source their copper from wires, tubes and whatever else is made of copper, I took an extra step in the process. I used this beautifully looking copper ore, which is called chalcantite. Essentially, it's nothing else than copper sulfate. And there are various ways to extract the copper, and I specifically used electrolysis, applying current to extract copper from the solution. I also used cementation, which is an exchange reaction between two metals, and direct smelting. And all of this to obtain 1 kilo of copper, which I then turned into bronze by adding tin to the molten metal. With all the metal ready, I was finally able to proceed with casting. Although there were some flaws, of course. The thing is, I am a curious person. I want to know what is inside the metal, stuff you don't see by naked eye. Fortunately, I don't need to destroy the knife to find out. To be honest, the casting wasn't successful on the first attempt, so I could take a cross-section from one of the failed attempts. But before we literally look inside the metal, is there a way to predict what we will see? I mean, I know the composition of the metal. The answer is yes, but there are some limitations. We can use so-called phase diagrams. Well, they may seem intimidating at the first. They are simply plots of temperature and composition. You can divide the plot into 3 parts. Everything above the liquidus line is molten metal. The region representing the coexistence of liquid and solid phases lies between the liquidus and solidus lines. And everything below the solidus line is a reaction occurring in the solid state, driven by diffusion. Here lies our composition, which intersects many lines. So what exactly happens when we pour the metal? First, we have molten metal of a specific composition. Then the crystallization begins. As you can see, there is a very narrow crystallization window, and during crystallization, the composition of the copper alpha crystals and the residual melt develops along those 2 lines. The crystals grow larger until they touch the solidus line, at which point all the melt is consumed, resulting in nice equiaxial hexagonal grains of alpha copper with 10% of tin. How is it possible that the starting crystals contained 3% of tin and now they have 10? Why is there no curing? The answer lies in diffusion. The growing crystals are in equilibrium with the surrounding melt, exchanging atoms and removing the concentration gradient. If we cool the metal even further, we should obtain both alpha and epsilon copper phase. But in reality, achieving this is very difficult. It simply takes too long. The problem is that all these theoretical concepts work only if you cool the molten metal super slowly. This is not the case for casting. So let's see what is really inside the metal. First, I need to make the piece manageable. I choose to encase the metal in epoxy resin. After curing, I roughly cut the sample and squared it on a milling machine. Now it's time for grinding and polishing. Once labeled, we are done. I'm using optical microscope and I'm working under reflected light. Let's start at the lowest magnification and take a little stroll around. Do you see those large dark colored spots? They indicate porosity, which is primarily distributed around the cross-section. Beside that, I can already see more than one phase in the metal. Now let's switch to higher magnification. It is clear now that there are some dark gray grains present. As we reach 200 magnification, there is much more to observe. Besides the copper grains and those dark gray grains, there's also some bluish material. Now we are working at maximum magnification. My guess is that the dark gray substance is copper sulfide, since I used copper sulfate as ore, which could be the source of sulfur contamination. There are also two other phases, which is pretty much everything we can see now. Fortunately, we can reveal some additional information through etching. I'm using a ferric chloride etchant mixture. A quick dip and we are done. You can already see that the surface looks different. Just for comparison, here we have unetched, lightly etched and heavily etched bronze samples. But let's get back to microscopy. Oh, did you see that? A crack, nicely along the grains. Well, let's continue in our work. Yeah, this is perfect spot. As you can see, the crystals are clearly cored, which means that the composition of the core and rim is different. And to prove this, I need to employ another method, electron microscopy, which will provide us with information about the chemical composition. This is typical example of image from a scanning electron microscope. If you are having a hard time linking those phases together, here is a little help. By the way, I checked the dark colored phase and it is indeed copper sulfide. The rest is, of course, copper tin based material with some iron. First of all, the grains are heavily cored. The cores contain 3.7% of tin, while the rims have around 13%. And between the copper grains is a tin-rich so-called delta phase, known for its light blue color. But how this structure happens? I was expecting a single homogeneous copper alpha phase. So what happened? Let's hear my interpretation. It all started with molten metal of this composition, then segregation of copper sulfide, which is no longer miscible with the metal, start of crystallization, which gives us those low tin cores. Since there is no time for diffusion, the growing grains become enriched in tin, leaving the residual melt depleted in copper. I was fortunate enough to find this casting adjust diagram, and as you can see, much more happens. We cross into the beta phase field during cooling. The last solid to form from the melt is the beta phase. From this point on, all reactions occur in the solid state, with no liquid present. The beta is no longer stable below 586 degrees, transforming into gamma phase and subsequently the delta phase, making the end of the reactions. By the way, you can stabilize the high temperature phase like beta by quenching, but that is not our case. So this is my proposal about what happened. And this is the resulting structure. And that's pretty much it. Yeah, I'm almost forget there's one interesting thing that I want to show you. Here at a lower magnification, the thing that you see are dendrites, which are the result of rapid crystallization. If you don't see them, I can help you. So keep in mind that we are working in 2D. This is discrete plane. We are not looking into, well, we are looking into 3D structure, but by 2D plane. So they appear like this. In 3D they look like this, essentially resembling snowflakes, I'd say, which is also unsurprisingly a result of rapid crystallization. I achieved similar result during electrolysis. That's it for today. Thank you for watching and till next time.